name is Frank Sanders. I'm the head of the Telecommunications Theory Division at the Institute for Telecommunication Sciences, a laboratory of the National Telecommunications and Information Administration, NTIA, located in Boulder, Colorado. Over the past 30 years, we've developed a series of techniques for measuring emissions from various types of radio emitters. In particular, we've developed techniques for measuring emissions from radar transmitters. In this series of talks, I will begin by describing the fundamentals of RF measurement techniques, and I will culminate the series by describing our techniques for measuring emissions from radar systems, techniques that hopefully you can implement yourself. Accompanying this series of talks are notes available on our website and also NTIA reports that you may find useful. We hope that you will enjoy watching this series of videos as much as we've enjoyed producing. Welcome to the 20th and last seminar in the ITS RF measurement series. The topic of today's talk is the calculation of antenna characteristics, meaning antenna directivity and antenna gain, from the configurations and dimensions of antennas. This is hopefully going to be a relatively short talk. I'm not going to use a lot of math in this talk, but I do want to use some mathematical results so that an engineer who either needs to identify a particular antenna configuration for a particular task, or an engineer who sees an antenna mounted on a ship or mounted on a building, mounted on a hilltop, and needs to try to infer from the antenna dimensions what the characteristics might be in terms of the antenna gain and directivity in space could do so based upon basically seeing the antenna configuration, having some idea what frequency it might be working at, and well, leave it at that. So some of the material that we're going to cover right now I've talked about in some of the previous talks, and just as an opener, several things about antennas. First of all, in terms of functionality, I'm not starting on. Here we go. In terms of sorry, I haven't had all my coffee. In terms of functionality, we have two major functions. One is that antennas, which of course are coupling energy in and out of circuits via free space, have to somehow match the impedance of a circuit, and typical circuit impedances are going to be 50 ohms, 75 ohms, or 300 ohms, and there are others obviously, but has to match the impedance of a circuit to the impedance of free space. And what's the impedance of free space? Anybody?
377 ohms.
377 ohms. So one way or the other, some kind of matching has to occur between the impedance of a circuit and the impedance of free space. The second thing that antennas do is to provide some sort of geometric directivity to the energy which is either being transmitted into space or being received from space. Now, the directivity could be essentially zero directivity, in which case we have an isotropic antenna that radiates and receives equally in all directions in space. But these are the two major things that are going to have to be accomplished by any particular antenna design. Now, basic antenna types. These are my breakdowns on antennas, basically three, and the third type sort of breaks out into a little bit of a 3A down here. But the first type, which I'm not going to talk about at all today, is an antenna that typically works at low frequencies, which couples energy between free space and a circuit via the B field component in an electromagnetic wave. And these are typically, but not always, basically toroids that have some kind of a winding on them. And these types of antennas are going to typically be used at low frequencies. We've used antennas like this to work down at frequencies of a few hertz or maybe even a few kilohertz. Second antenna type is an antenna which is a design that is based on tuned elements, and I'll put that in parentheses. It could be a single element or multiple elements. These antennas include, but are not limited to,
dipole antennas, stacked dipole antennas, oh yeah, and Yagis, which are narrowband antenna designs, as are dipoles, narrowband, and stacked dipoles, narrowband. They're inherently narrowband because they're built out of one or more elements which are in fact tuned to the wavelength of the frequency that they are supposed to interact with. And then finally log periodic antennas, and these are by definition wideband. And the reason that they're wideband is, unlike a Yagi antenna, which if you see it will look like this, seen from the top or seen from the side, in which the element size and the spacing, between the elements, which I've tried to draw as a constant, is adjusted for a single frequency. With a log periodic, we have an antenna design which consists of a set of elements that vary in size down the length of the antenna. So here we have a group of elements that are tuned to a variety of frequencies, and hence is wideband. Now, in contrast to the tuned element designs, we have antennas that consist of physical apertures, and these are the ones that we're going to be most concerned with in this particular talk. And these include antennas that use parabolic, dish, that is, reflectors, which focus energy on a point in space where we place an antenna that actually receives energy. I'll draw a picture of one of these in a moment. And also horn antennas. And these antennas have non-zero physical apertures that are actually capturing energy from space. And finally, I'm going to draw it like this, I'll make it 3A, we have phased array antennas. I'll call them arrays, or phased arrays. Phased arrays. And these can be a bit of a cross between the tuned element designs and the physical apertures, in that in a phased array antenna, which I'm going to draw as a plate with a lot of elements on it, we could, for example, mount a whole set of dipole elements, like so. And the antenna functions, and we've talked about this in previous talks, by phasing the energy from one element to the next, such as to produce a planar wavefront at a distance out in front of the antenna, which can be directed in space electronically. Or we can actually build an antenna out of little slots. And I'm intentionally drawing these at an angle because how we design it is really completely arbitrary in many respects. But we can design an array of slots. In any event, to some extent, this array works like a physical array. It does have a nice finite size that captures energy, but on the other hand, functionally speaking, it's working as an array of individual elements, which may well actually be basically tuned elements. For example, I've seen some large phased array antennas on the PavePause radar, which we've seen in one of the previous talks. It's a 10-story tall building, which has about 1,700 crossed dipoles mounted on the face. So leave it at that for the moment. One of the things that I would like to distinguish momentarily between antenna versus reflector is on a parabola. And we often talk about a parabolic antenna, or an antenna with a parabolic reflector, and of course we can have the reflectors which are not necessarily parabolas, but which instead are shaped somewhat like this and have a reflecting surface like so, which I'll elaborate on in a moment. What we typically have on the antenna is a reflector, which I'm going to draw in 3 dimensions like this. So here's the side or the back of the reflector coming back in like this. So we have a dish scooped out here, and this is technically not the antenna. This is the reflector. The antenna, to be more correct or more precise, is going to be an element or a set of elements which, for example, could be a log periodic array, which is mounted here mechanically, like so, at the so-called feed point, and this thing is actually mounted structurally onto the reflector like so. And the concept to draw this antenna in cross-section is as follows. Here's the parabola seen with exaggerated curvature from the side, and rays that enter the parabola parallel to each other are reflected back up to a common point in space, and that point in space is where we mount an antenna, which could, if we want this to be a wideband system, for example, be a log periodic array like so, and then the energy is coupled from the dish down into a circuit of some sort. So technically this is the reflector, technically that's the antenna, but oftentimes people simply refer to these as parabolic dish antennas. Same thing for an array like this. Here the feed gets mounted out in front of the antenna reflector like so. And you see these on the FAA air traffic control radars. We've seen these, for example, on the ASRs in the earlier slideshows in this series. But the concept is the same. The energy is focused down to this point where an antenna is located. However, typically on these antennas, and also sometimes on the parabolic dish antennas, we don't necessarily use a log periodic. We could use instead a horn configuration, and this segues nicely into the next thing I'll mention. Try to draw this a little bit in 3D here, like so. Here's our horn coming back like that, and again, the horn will feed down into the actual circuit where a receiver or a transmitter is located. But a horn, of course, is just that. It is typically a rectangular aperture seen in cross-section. It'll look like this. And it is typically, but not always, built in a flared configuration like this. Like so. Try to draw it in 3 dimensions here. And I'll talk about more about this in a moment. But both the horns and the parabolas have physical capture areas that can and do intercept energy traveling through space in this physical aperture. So now, I mentioned that in addition to matching the impedance between free space and a circuit, antennas have directivity. In an earlier talk in the series, we discussed the case in which the directivity of an antenna or of any radiation in space is completely equal in all directions. This is isotropic, like so. And here I'm going to draw the surface of a sphere like this, and we have equal directivity in all directions in space, in and out of the sphere. Isotropic. I do not believe that any isotropic antenna has ever been physically realized as such. It has occurred to me that if we heat a piece of metal to a high temperature and let it radiate, that it will radiate isotropically. But in terms of building a practical antenna, the problem with building something that would be truly isotropic is that somewhere, somehow, you would have to get energy in and out of the antenna through a circuit connection, and it would be probably hard to do that in a pure sense without somehow disturbing the overall isotropic characteristic of the antenna. But it is possible to come close. Most antennas, however, do have a pattern of radiation reception and transmission into space, which looks somewhat non-isotropic. For a dipole, the pattern looks like this. We can build the dipole in here like so. And we've talked in just the last talk about, for example, the efficacy of using the nulls in a dipole pattern for direction finding. Dish antennas and horn antennas, here's a dish, will have some kind of a directive pattern that looks something like this. And then inevitably, even though they're not desired, there will be non-zero side lobe structures. Here's the main beam. Same thing for horn antennas. Here's a horn seen from above or from the side, as the case might be. And again, the horn is going to have some kind of directivity in space. And this is obviously a geometric characteristic of an antenna as opposed to an electrical characteristic that we get with the impedance matching. I mention this because the way that I like to treat antennas, in any event, is as apertures that interact with waves. So, apertures interacting with waves. We imagine and I'm going to construct what I'm going to do here is I'm going to construct a bit of a theoretical model for an antenna behavior, and then we'll compare this to real-world antennas, and we'll finally end up by calculating the characteristics of the antennas. Imagine that we build a wall, and the wall has a slot in it like this, and it's a small slot right here, little narrow slot, and the rest of this wall is impermeable to radiation. And on one side of the wall, there is a wave which propagates toward the wall like so. And what I'm drawing here are successive wave crests or wave troughs. And of course, as the energy emerges from the wall and we draw the wave crests or wave troughs, the spacing between the troughs on this side is the same as the spacing on this side. But what emerges from the wall are a set of spherically oriented wave fronts. And of course, this is a Huygens wave front coming out. And we can imagine equally well that if we cut a second slit in the wall right here, then both slits independently behave the same as a single slit would. And so we get two sets of Huygens wavelets coming out, like so. And again, I'm drawing the crests of the wave fronts. So this is a classic diagram, of course, from physics textbooks. And the result is that if we have a screen set up here at a distance, and we plot the intensity of the energy on the screen, say for this double slit system, we'll get a set of maxima and minima like this. Where I'm plotting on this axis the intensity of the radiation that's falling on the screen from the two slits, and of course this is a two-slit diffraction pattern. Two-slit diffraction. Again, nothing you don't know or haven't seen here, I will assume. Now. We assume here that the slit has essentially zero size, essentially zero width, that the size of the slit is small compared to the wavelength of the radiation. We know that if we build a physical aperture with a physically large slit like this, that we can model it theoretically as a set of these arbitrarily small slits like I've drawn here, and that if the spacing between these arbitrarily narrowly spaced theoretical divisions of this physical slit is labeled as D, then if we blow up this part of the diagram, what we get is a geometry that looks like this, where we have wave energy emerging at some angle theta, like this. And here's D. I'm expanding D out. I'm zooming out on it like this. We zoom out like this. So here's D. And we have energy emerging here, like so. And we'll draw a normal down like this. So we get the same angle theta here as we get here. And we know that we get a path length difference. Between this point and this point, between two successive points, which is equal to d, this spacing that we can make arbitrarily small, d times the sine of theta. And it's this path length difference between adjacent points in our theoretically constructed slit that results in the diffraction pattern that's produced. Okay, so again, so far so good. Now, imagine as the board rolls forward, imagine that we treat an antenna as if it were a slit with a finite size, like I just drew, which is acting as an aperture for wave radiation. Well, it turns out that that's, number one, that's a pretty good model. And number two, if we draw diffraction patterns relative to, and here's how I want to do this. We imagine that we have a slit here, like I drew on the previous board. The slit has some size. It could be a double slit, but we'll draw it like this. And imagine that we move out in front of this slit, which we're going to model as our antenna. Here's our slit, which is going to be functionally equivalent to an antenna, because an antenna is an aperture and it radiates or absorbs wave radiation. So put some kind of an antenna in here, let it go ahead and radiate like this. We imagine that we then put screens in front of the slit. Actually, I'm going to use one screen. We put it at some distance in front of the slit, which is equal to R1, and then we move our projection screen out to a second distance, R2, and then we move it out to another distance, R3, and so forth on out. And we're going to plot the diffraction pattern that falls on the slit as we start out close to our antenna, and then as we move our projection screen further and further out away from the antenna. And what happens is, when we're at a distance R1, which I'll draw here like this, we will see a diffraction pattern which looks somewhat like this. And down. And this pattern is described mathematically by Fresnel equations. And then we move out to a distance R2. And at a distance R2, we're going to get a similar but different looking pattern, which is going to look like this. And so forth. And then we move out to a further, larger distance, R3. We get a pattern that's going to look something like this. And finally, as we move out in distance, we're going to find that these patterns, these projection patterns, these diffraction patterns that we get from this, our virtual antenna, are going to approach a pattern that looks like this. One big lobe with little small lobes, and where all of these patterns up to this point, all of these patterns that are in fairly close to the antenna, and I'll define close in a moment, are described by the Fresnel relationships, which are exact solutions or equations to this diffraction problem. We find that as we move out to a large distance, and again I'll define this in what this distance is in just a moment, we find that the diffraction patterns begin to converge to this pattern as we move out to arbitrarily large distances. And this is the solution that occurs as we approach an infinite distance from the screen. And this is described by the Fraunhofer approximation to the Fresnel equation. And this approximation gets better and better as the distance from the slit from our so-called antenna begins to approach infinity. Now, geometrically what's happening is, as we move further and further out away from this antenna, the radiation wave front is basically looking less and less spherical, and instead is approaching something that looks like a flat planar wave front. One way to think about this is radiation is coming from a distant star. At the distance between us and, say, Alpha Centauri, the radiation that is arriving at the Earth from Alpha Centauri is virtually a flat plane wave. Now, the question is, how far away do we need to go before we arrive at this nice flat planar wave solution which behaves basically perfectly like this Fraunhofer approximation of the Fresnel equation, which really technically only occurs at infinity? Well, the short answer is that, strictly speaking, you never get there. Strictly speaking, any distance is less than infinity. But as a practical matter, the so-called far field approximation for an antenna pattern, because that's what we're talking about, is the pattern that we converge on as the final pattern that we see at virtually basically any distance away from the antenna as we go out to distances approaching infinity, is going to occur at a distance which is equal to, and there are two different criteria for this. If you're more liberal, you'll say that it occurs at a distance of d squared over lambda, and if you're more conservative, you'll say that this limit occurs at 2d squared over lambda. Bear in mind that you never really get there, but d squared over lambda or 2d squared over lambda, where lambda is the wavelength of the radiation that is coming out of the antenna, and d is the antenna's physical aperture diameter. So d squared over lambda or 2d squared over lambda. If you're doing a measurement and you need to get into the far field of an antenna, you could probably justify either of these. Any distance beyond d squared over lambda or 2d squared over lambda is probably going to be accepted by almost anyone as having been in the far field. And by the way, the so-called near field patterns for an antenna are related to the far field patterns by the Fourier transform. So we can Fourier transform the near field to get to the far field, or inverse Fourier transform to move between the two. So technically, if you make a measurement of an antenna pattern in a near field, you can calculate the far field or vice versa. People like to work typically in the far field of antennas because they can assume that they're getting a plane wave out in the far field. Now, one thing that I think is very significant about the comment that I just made is that the behavior of an antenna, geometrically speaking, in terms of the field that it produces in space, is a function, the antenna behavior, geometrically, is a function of the behavior, is a function of the variables of both the aperture size, d, and the wavelength of the radiation that we're working with, lambda. Now, one thing that I think is worth remembering is that any time that radiation with a wavelength lambda, which I'm going to arbitrarily draw like this, interacts with a physical object, which I'm going to draw like this, if the wavelength of the radiation is commensurate with or substantially larger than the size of an object with which the radiation interacts, the object is not going to produce a strong amount of directionality of that radiation in space. Here's an example. You can still hear me when I turn my back to you. The reason that you can hear me when I turn my back to you is that the acoustic waves that my mouth is generating are substantially longer in wavelength than the size of my mouth. And so when my mouth is running like this, here are my lips, sort of Pac-Man lips, I'm producing this sort of Huygens wavefront, which actually, and I'll go up and do a crude drawing of my nose, and here's my eye, and here's my forehead, and here's my neck coming back down and around like this, and here's my chin, and coming back down and around like this. The energy is actually going to diffract all the way back around my head. If, on the other hand, I could produce acoustic waves that were small in wavelength compared to the size of my mouth, I could beam my voice out like a microwave beam coming out of a dish antenna where the parabola would be substantially larger than the wavelength, and I could actually beam the radiation at you, and if I were looking at you, you could hear me, and if I turned away, you wouldn't be able to hear me. But to do that, I'd either have to have a much bigger mouth, it's hard to believe that that could be possible, or produce waves that were much, much smaller compared to the size of my mouth in order to beam the energy around in space. So, another place where we see this phenomenon occur is the wavelengths of visible light when they interact with water droplets in the Earth's atmosphere. Here we have a lot of little water droplets in the Earth's atmosphere. And these water droplets are actually fairly small in size compared to the wavelength of visible light. We covered this in an earlier talk. Typical wavelength for visible light is what, 5,000 angstroms if we're looking at green light, for example. The visible spectrum runs from basically, give or take, around 4,000 angstroms to around, we'll say 6,000 angstroms, just in round numbers. Water droplets have sizes that are small compared to the wavelength of visible light. As a result, if we have a lot of these droplets arranged in a cloud in the Earth's atmosphere, what happens is all of these water droplets diffract the energy in a highly non-directional way, and the result is that we see the energy scattered. And I'm going to do a crude drawing of a cloud in the sky. Not that crude. We'll draw a thunderhead. Here's a thundercloud seen in cross section on a hot summer day, and we see this thing as appearing white because it consists of water droplets that are scattering all of the energy in visible light at all frequencies in visible light, basically equally in all directions, and the result is that we're seeing white. And of course the reason that the sky is blue is because the oxygen molecules, which again are much smaller than the wavelength of visible light, are scattering light via Rayleigh scattering, and the blue light is more strongly scattered. The short wavelengths are more strongly scattered by the diatomic oxygen in the Earth's atmosphere than the longer wavelengths, and so we have Rayleigh scattering, which makes the sky blue. So there, now you've heard the explanation for why is the sky blue. But in all of these cases, the energy is being scattered by and is interacting with elements that are much, much smaller, my mouth, water molecules, diatomic oxygen, than the wavelength of the radiation itself. The situation changes when radiation interacts with objects that are somewhat larger than a wavelength. When energy is interacting with objects that are substantially larger than its wavelength, then the object, whether it's a parabolic reflector or some kind of geometrically constructed device, becomes capable of strongly directing energy in space. So here we'll draw a parabolic reflector like this, and we'll draw the wavelength of the radiation that's going to interact with it like that. So here's this little tiny lambda down here interacting with this rather large reflector. When this occurs, geometrically it's possible for this reflector to produce a fairly strongly directional beam in space. It's really as simple as that. Now, it's interesting, though, and informative, to have some idea of what these wavelengths are for electromagnetic radiation. So I'll do a little drawing here, not a drawing, a graph, not a graph, a table, excuse me. We'll do frequency, and then we'll do lambda. And we'll do this for 1 megahertz, 10 megahertz, 100 megahertz, 1,000 megahertz, gigahertz, and finally we'll just do 10 gigahertz, like so. We want to know this because we want to know what size antenna we would need to build in order to produce fairly strongly directional beams for any particular frequency that we might ever need to work at. So the wavelength lambda is going to be equal to the speed of light divided by the frequency, nu, in this case. Speed of light is 3 times 10 to the 8 meters per second, so 1 megahertz is going to be 300 meters in wavelength, and then I intentionally did this as a log progression. 30 meters, 3 meters, 30 centimeters, basically about 1 foot at this point, and finally 3 centimeters. And based on the description that I just gave, if we want to direct this energy strongly in space, we're either going to need to build a parabolic reflector at any given frequency, which is substantially larger than this wavelength lambda, or equivalently, we may want to build some kind of a phased array, but even if we want to do that, the phased array size overall is going to have to be, and I'm drawing a phased array with elements on the face, the phased array size is still going to need to be rather large compared to the wavelength of the radiation that we're working with. So, suppose that we want to build a space search radar like PavePause. We decide that 400 megahertz frequency, which is between here and here, is a good frequency to use in terms of propagating through the Earth's atmosphere and interacting with objects in space. But we need the big antenna that we're going to build at 400 megahertz to be substantially larger than a wavelength. Well, that means that it's going to have to be substantially larger than at least a few meters. And in fact, we know that the PavePause radar, we've seen photographs of it earlier in the series, is a building that's 10 stories tall. Basically, it has to be a large building because it's working at a relatively low frequency. On the other hand, we say that, for example, we need to operate an airborne radar. This airborne radar needs to have a highly directional beam, and it needs to fit inside the nose of an airplane or inside the belly of an airplane. Is this going to work well if we try to build a radar down at 1 megahertz? No. Lambda is too large. Airplanes aren't 300 meters long. Airplane antennas that go inside airplanes aren't going to be 30 meters in size. Even 3 meters in size is a push, although Navy AWACS planes work with radars at about 400 megahertz. But more practically, these are the wavelengths where we can build fairly compact antennas that are well adapted for fitting inside aircraft, spacecraft, small boats, small vessels. And aside from propagation characteristics, that's why these frequencies from 1,000 megahertz upward to 10 gigahertz and above are considered highly desirable for radar systems. It's because we can build relatively small antennas, which are nevertheless large compared to a wavelength of the radiation that they're interacting with. So, again, it's basically as simple as that. The other thing that we can do is to use this information to look at a dipole antenna and tell, by looking at the dipole antenna, assuming it's a half-wave dipole, roughly what frequency it might be working at, because just to expand part of this table a little bit, we can look at 300 megahertz frequency, 400 megahertz, say 800 megahertz, and what is lambda and what is lambda over 2 at these frequencies. We'll say that we're looking at a Yagi, or we need to build a Yagi antenna, or a dipole that's going to work at these frequencies. And we get a wavelength of 1 meter, 75 centimeters, and basically 38 centimeters. And if we divide these numbers by 2, we get half a meter. We get about 38 centimeters, and finally we get about 18 centimeters here in round numbers. So if we're looking at either a conventional dipole antenna or a Yagi antenna that has a set of elements mounted on it, we can quickly estimate what frequency it must be operating at just by looking at the size of the antenna. Again, conversely, if we need to build a Yagi to work at these frequencies, we know immediately roughly how large the how large, how long the elements are going to need to be, because these elements are in fact tuned elements, tuned to these frequencies, tuned to these wavelengths. So fairly straightforward. An easy way to remember all that is 300 megahertz is going to produce a 1 meter wavelength, because the speed of light is 3 times 10 to the 8 meters per second. Now, believe it or not, we're actually close to being done. I want to talk about directivity, which I'll write as D, versus gain, G. Directivity is equal to the directivity of an antenna. If we're talking about beaming energy into space, receiving energy from space, the directivity of an antenna is going to be equal to the power density in some lobe or beam coming out of that antenna divided by the power density that would have been produced had we been using an isotropic antenna. So it's the difference between what the antenna is actually putting into space in a direction versus what the antenna would have been putting into space if it had radiated energy equally in all directions in space over the surface of a big sphere. And well, I'll leave it at that. Now, gain is equal to the directivity of an antenna multiplied by the actual electrical efficiency of the antenna in terms of energy that's coupled from a circuit. This is dependent entirely on energy in space divided by the energy that would have occurred in space due to an isotropic radiation pattern. Directivity. Gain is directivity multiplied by whatever the efficiency of the antenna is in terms of coupling energy in and out of a circuit. This is a more practical number to use because generally what happens is if we hook up an antenna and we run it into some kind of a circuit over here and we're measuring power coming in or out of the antenna, we're going to do it in or out of this circuit with the circuit hooked up to some kind of a power meter, which in principle has some kind of a needle that shows us the amount of power in a circuit like so. So it's as simple as that. So gain is a geometric effect. It's related to directivity, but technically we have this little factor A to put in. Now, the definition of the effective aperture, A sub E, this is definitional. There are justifications for the definition. I'm not going to go into them here. But by definition, the effective aperture of an isotropic antenna is equal to the wavelength of the radiation that's coming in or out of it squared, lambda squared, times G divided by 4 pi. 4 pi is, again, a geometrical feature related to the fact that there are 4 pi steradians in a sphere, or in a spherical distribution, in a distribution of, well, I was going to say spherical distribution of energy, but really a spherical distribution of anything. There are 4 pi steradians in a sphere, period. Okay, so lambda squared times G over 4 pi. Now, this is definitional. What this says is, well, I'll leave it at that. But suppose that we want to represent the effective aperture of an isotropic antenna in a propagation calculation. We've done this in an earlier talk in the series, such that we're going to work in decibels. And so at some point in our calculation, we have to take 10 log of A sub E. Well, that's going to be equal to 10 log of lambda squared, which is 20 log lambda, plus 10 log of the linear gain, minus 10 log of 4 pi. Now, rather than work in terms of wavelength, we typically like to work in terms of frequency. And remember that lambda is equal to C divided by nu, or here I'm just going to write F for frequency. And so this means that the effective aperture in decibels written in capital letters, which is equal to 10 log A sub E, is equal to 20 log of the speed of light, so that's a constant, minus, this is important, minus 20 log f, plus 10 log of little g, which is big G. The convention that I've always used is that any parameter appearing in capital letters is a decibel quantity. If it's in lowercase, it's a linear quantity, minus 10 log of 4 pi. And here's where I'm going with this. Here's where I'm going with this. This is a constant. This term is a constant. And so that means that we have some constant terms that we pull together. Then we'll go ahead and add big G, the gain in, and this is gain in decibels relative to isotropic. People often write the gain of an antenna as just dB, but it's usually decibels relative to isotropic. Now, if they're comparing it to a real engineered constructed antenna, then they're typically comparing it to a dipole, in which case it'll be decibels relative to a dipole, which is dBd, but we'll leave it as dBi here. And then, and this is the tricky part I want to come to, minus 20 log of the frequency. So the functional dependence for the effective aperture of an isotropic antenna, which we're never going to actually build, it is going to be some kind of a constant plus its gain in dBi. And by the way, we can relate this to the gain of a physical antenna, a dipole, which we would write as decibels relative to a dipole, by a factor of 2.1 dB. A dipole should have a gain of 2.1 dB over isotropic, minus this term, minus 20 log f. This term for the effective aperture of an isotropic antenna, or equivalently even for a dipole gain, when it appears in calculations related to propagation, will show up in the calculation, and I have on numerous occasions heard people say, oh, we don't want to work at 9 gigahertz or we don't want to work at 5 gigahertz because we don't want to have to deal with all that loss at those high frequencies. This equation has nothing to do with loss at high frequencies. This has to do with the definition of the effective aperture of an isotropic antenna, which is decreasing as frequency increases, and there is no relationship between this and the loss through space. Space always results in the decrease in the intensity of a wave as a function of the distance from the source of the radiation squared, period. It's geometrical. Space doesn't know anything about frequencies. So when you see this, if you ever see it, please don't tell me that you don't want to work at 9 gigahertz because of that 20 log f loss that you get at 9 gigahertz. It has nothing to do with 9 gigahertz, has nothing to do with the antenna. In fact, as we'll see in a moment, the effective aperture of a dish antenna goes up at the rate of 20 log relative to isotropic, which means that it's flat because it's the effective aperture of an isotropic antenna, which is actually dropping as 20 log of the frequency. Okay, so just like to point out that. So we imagine that we're going to build a directional antenna. It's going to radiate energy in some sector in space. I draw a sphere here, and then on this sphere I draw a little rectangularly shaped zone which measures 1 degree by 1 degree, like so. And how many of these little 1 degree squares fit onto the surface of a sphere? And the answer is 41,000, check my numbers, yeah, 41,253 of these little 1 degree sized areas on the surface of a sphere. So if we can collect all of the energy coming out of a radiator here and direct all of that energy into this 1 degree zone, like so, radiating out into space, then we will have concentrated the energy coming out of that radiator relative to having distributed it over the surface of a sphere by a factor of 41,253. So the gain of that antenna would be equal to 41,253 divided by 1. Basically, this is a sort of, if you will, it's a sort of an amplification factor in terms of squeezing the energy down onto a single azimuth. And 10 log of 41,253 would give us the gain of this antenna in decibels, and that is, I think, 46 dB. I'm checking my notes. Yes, 46 dB, like so. So a geometric gain factor of 46 dB over isotropic means that we're squeezing all the energy down into 1 square degree in space. That's kind of an interesting or useful mnemonic. Now, if we more accurately model this not as a rectangular zone, but as a zone with a little circular cross section, like so, then the number changes slightly, and what we get is that G is equal to 41,253 times 4 over pi, and that's equal to 52,525, 52525, and 10 log of that number, which I think I did. I didn't actually do it. It's going to be just slightly larger. It's going to be about 47 dB. So it doesn't make a huge amount of difference. But if we can squeeze, again, if we can squeeze the energy down to one square degree, we get about that. Now, real antennas are not able to squeeze all the energy into a single zone like this with no other energy radiated in any other direction. I've already alluded to the fact that the real radiation pattern of an antenna is going to look something like this. Typically, the first side lobe on either side is going to be the highest, but that can vary. But we do have energy coming out in these other lobes, and this represents a loss in efficiency for the antenna. And a typical realistic efficiency for an antenna, realistically, compared to an antenna that can theoretically perfectly guide and direct all the energy in space, is about 55%. So now we can put, believe it or not, we can put the whole picture together. We understand the relationship between directivity and gain. We know that a typical efficiency, I'm just going to state it, I'm not going to prove it, a typical achievable efficiency is about 55%. In other words, of all the energy that this radiator is producing, about 55% of it is coming out in this main beam, and the remaining 45% is distributed all the way around here in the side lobes and back lobes. So what we can do is actually draw up a little table where we write down the aperture of the antenna. I'm going to go ahead and erase this. And then I'm going to write the beam width as a function of the aperture. And we're going to do all of our calculations in natural units. We're not going to use meters or centimeters. We'll do all the calculations in terms of wavelength. The wavelength lambda, whatever wavelength we pick, is going to be our unit of measure for these calculations. And then we have directive gain as a function of the aperture. And then lastly, we have the gain itself, gain, as a function of the beam width. And I'm going to do this for the two most basic physical apertures that we will ever encounter: a horn aperture, a rectangular aperture on the end of a horn, and a circular aperture of a parabolic reflector. Do it like this. You need a little space here, as we'll see in a moment. And so, and then we're going to divide it right down the middle. For, first of all, a horn, and we've got two dimensions that we're going to consider for this horn. I'm going to draw the horn twice. We're going to consider the effective aperture of what we'll call, well, not call, but what is, the E field interaction for the horn. We'll call it vertical, and the effective aperture for the H field for the horn. This will be the horizontal dimension on this thing. And for the parabola, we'll look at it face on, and we'll just say that it has an aperture A. And so we have every beam that we draw has two dimensions with an X and a Y, and we're just going to write these as theta 1, say for the X, and theta 2 for the Y. These are angular beam dimensions. If the beam has a circular cross section, then theta 1 is equal to theta 2, but it doesn't have to have a circular cross section, and theta 1 don't have to equal theta 2, but the area of the beam is basically going to be the product of these two. So theta 1, and we could go through the math on this, but we're not going to. Theta 1 is equal to 50, roughly, at 55%. At 55% to 60% efficiency. So this is for real antennas, real live antennas with 55 to 60% efficiency. Theta 2 is equal to 67 lambda over A sub E and A sub H, respectively. And down here, we'll say that theta 1 and theta 2 are in fact equal to each other, and they're both equal to 72 times lambda divided by the diameter A. We're just assuming symmetry on the dish here. Divided by the diameter A. Again, that's for real world efficiency. And so this means that, as it turns out, the gain is equal to 7.5 times A sub E times A sub H divided by lambda. That's linear gain. That means that the decibel gain is equal to some constant. We just take 10 log of G. It's going to be equal to some constant plus 10 log of A sub E plus 10 log of A sub H plus 10 log of F. And finally, if we want to look at the gain as a function of these beam widths, it turns out it's equal to about 31,000 divided by the product of the beam widths theta 1 and theta 2. And finally, for the dish, the linear gain is equal to about, these are all about because these are approximations for this efficiency, 5 times 8 times, 5a squared over lambda squared. And that means that the decibel gain is equal to a constant, again we take 10 log of little g, a constant plus 20 log A plus, 20 log A plus 20 log F. Remember, F goes inversely as lambda. It would be minus 20 log of lambda, so it becomes 20 log, so it becomes plus 20 log F squared, squared. Lambda squared here, 5a squared over lambda squared. So the lambda squared goes to 20 log F. And look at that. Remember that the effective aperture of the isotropic antenna dropped as minus 20 log F? Well, the gain of the dish relative to isotropic goes up as 20 log F. In other words, in real terms, in terms of the aperture being presented, it's a constant aperture antenna. That's consistent with the fact that, in fact, the aperture of this dish is constant. In other words, this flattens out the minus 20 log F that we see come out of the calculation for the effective aperture of an isotropic antenna. And functionally, the linear gain of the antenna is about 27,000 divided by, assuming that these two are equal to each other, divided by the beam width theta squared. Simple as that. And that basically concludes the talk. Anytime that you see an antenna, either a horn antenna or a parabolic dish antenna or even a radar antenna that's a sort of a cosecant squared, you can roughly calculate the gain if you know what wavelength it's working at, or you can work the relationship backward if you know the wavelength but you don't know the gain. You need to know one or the other, but if you know one or the other, you can back calculate the other one. This also explains, again, why we don't typically build dish antennas to operate at 10 megahertz. We do have dish antennas at the Department of Commerce Table Mountain field site which will function at frequencies of a few hundred megahertz, and those antennas are 60 feet in diameter. I hesitate because I'm thinking 60 meters, but they're about 60 feet in diameter. So that's probably about the largest size dish that can be practically built as a steerable dish. The Arecibo dish in Puerto Rico, which is not steerable, could work at even lower frequencies. But basically, these are the relationships between beam width and gain as a function of aperture and gain as a function of beam width. So with this, as I say, you should be able to either calculate the size antenna you need for a given application, or if you're working with an established antenna, you can establish what the gain or the wavelength is that the antenna is using if you know one of those parameters or the other. Any questions? Well, thanks for bearing with me. Hopefully some of this will come in handy at some point or another in your career. Thanks very much.